Okay, we'll call this Gauss's law in spherical symmetry. Oh, we just use that as an example. So here, let's say that we have do a couple different problems for spherical symmetry. We'll start with an insulator. So let's say that this is something like a rubber ball, and we take the charge and we give it a uniform charge density, volume charge density, that is dispersed uniformly throughout the whole volume of the sphere, on the surface and everywhere inside. So, and we want to find a field three places. And so let's say that the sphere has a radius r, and we want to find the field outside of the spherical charge distribution, that is, for a distance. Let's say that the radius is r naught. Let's make it a capital R naught. And we want to find the field at a distance r is greater than r naught. Then, so what that means outside the sphere. Then r equals r naught, so that's on the surface, and then r less than r naught. Three different problems, essentially, in three different places. But let's set up the problem like that. So consider a uniform charge distribution. Volume charge distribution. Uniform spherical. Of radius r naught and uniform charge density rho naught. Find the field, three places. First place is going to be E or R greater than R naught. And E equals R naught. Then inside the charge distribution, that's R. That's That's how you might see the problem stated. And here we can draw the charge distribution. So we'll make it. So I'm going to redraw it up here 3 times. So let's just. Circular look. And, I kind of want to give it some sort of. It's a sphere, so it's no way to really draw it. Hard to give it perspective, but the charge is all over the thing. A little warp ball. Some sort of, I don't know, perspective, maybe. 3-dimensionality. So it's solid. That's the point. Now, I'm going to go ahead and remind you of the rules for applying Gauss's law. I'm pretty sure I wrote them down the other day, but I'm not forming a visual in my mind. Let me do that for you again. To get the ink straight on this thing. So, part 1. So here's our little ball here. Let me draw it over here. Now, this distance here, as we said, is R naught. In fact, I'm going to try to use a different color. Actually, I'm going to make that all better. All right. See it better. History. Okay. So, we can put out some rules for applying Gauss's law. Let's do them over here. Well, yeah. So So basically 4 or 5 different ones. Determine, evaluate charge distribution, or determine, or identify, like that. Identify charge distribution. Identify field pattern. E field. Actually, I could put identify charge distribution symmetry as well, but that's, I guess it's there. And then same thing with the field. Identify field, E field, pattern, or symmetry pattern. E field pattern, symmetry. Then choose your Gaussian surface. Gaussian. And that Gaussian has to match symmetry of the charge distribution. And it needs to go through the point where you want to find the field. So, you can say something like place a Gaussian through R. And then apply Gauss's law. And then solve for E. I usually write it out like that in 5 steps. Okay. Now the first 2 steps, I'm using the word identify just because I want to emphasize to you that there's nothing really to calculate. You're not calculating anything in the first 2 steps. You're just basically evaluating the thing, that you have to solve for, the charge distribution, the symmetry of it. So this thing is basically like a solid ball. And it has the charge all through it, uniformly distributed all through the inside. And we've written it here, but we could represent it up here, written it here, right? And this is the radius. But over here, you would see something like maybe the rho naught would be something like, pointing to the ball and implying that it's also inside, I don't know, something like that. We generally use rho for spherical symmetry, gamma, sigma for area. So not spherical symmetry, I'm sorry. Rho for volume, gamma or sigma for area, and lambda for length when we're using charge density. In fact, I used lambda for the previous problems we did with the linear symmetry. I'll write that once I do this problem. Running. So we want to find outside the first field. Okay, so what we do then is we find any position outside the sphere, and we're measuring from the center of the sphere. So, R might look something like that. So that's going to be point P. We want to find the field right at that point. Well, Gauss's law involved covering the charge distribution within some, well, actually, I didn't do all of 1 and 2, but that is where we want to find it. And that thing has a distance of small r is the length of that thing. Okay, the point's there. Guess I could put a vector symbol on that. Now, parts 1 and 2, we have the charge distribution. So what would the field associated with that charge distribution look like? Well, the field is going to be radial. It's going to point from the center out radially away from the distribution. Now, I'm just going to draw it from the surface because on the inside, the functional form may be something different, but we definitely know that field lines have to terminate on the surface of the object. So there would be, we can find out whether there's going to be a field on the inside, but clearly, actually, that's going to be different, confusing. So we just use a different color for the field lines. I guess most people would use red, same as the charge distribution. So why don't I do that? So the field lines are going to be radially outward, and they have to terminate on the surface. Remember, we said that field positive charge is the origin of an electric field. We have one field line that's going to go directly through that point, right? But we want to know the value of the field at that point. Now you can see that we can see that the density of the lines, now we actually know we know what we should get. Because for a spherical charge distribution, we've already shown with Coulomb's law, well, we showed with a point charge, be careful, we didn't show with but that the value of the field, any field distribution, when you get far enough away from it, it looks like a point charge. Point charge is spherical distribution. And so what we would expect is something that has the form Q or K, Q over R squared. Now, everything that we've done, no matter how complex those other problems we did, once we scanned out far enough where the distance was much larger than the diameter or the geometry, so any geometry associated with the charge distribution, it's always going to start to look like a small little circular point charge, right? So we should get that approximation far field approximation, as they called it. far field and near field approximation. But here, the whole thing is spherical. It's spherical as a spherical distribution, so that should be the answer anywhere. And we see that pattern where the density of the field lines decreases as you move farther away, and we could calculate and show that. And so we know that the number density, the line density of fields is proportional to the magnitude of the field. And so since the line density is diminishing, number of lines the same, but the cross-sectional area, let's say, or the sphere, if we, enclose it in a sphere, I showed you that, a while back, that the number of lines per unit volume is going to decrease because the volume is getting larger, and you're dividing by the volume. Lines per unit volume, per meter, lines per meter cubed. So we've only got 8 lines, well, represented here. So 8 divided by larger and larger numbers is going to ultimately go to 0, because as R goes out to 0, since the volume of a cube is R cubed. No, sorry, it's 4/3 R cubed. Then as you go out farther, then you're going to be dividing by basically infinity or a large number. Anyway, we talked about that reason already. But yeah, so that's the first 2 steps. We have a spherical charge distribution, and we have a radial electric field pattern. Step 3, choose your Gaussian. Well, your Gaussian should match the symmetry, usually in some way, of the charge distribution. So if I choose spherical Gaussian surface, and remember, a Gaussian is like a net, kind of like a fisher's net, or a a net made of mesh or spider web or something like that, where you can mold it however you want. And you always have to enclose the charge distribution if you want to, And so if we make it a field, if we make it a sphere, and we center that Gaussian over our charge distribution, so that the center of the charge distribution is also the center of the Gaussian, then from a cross-sectional point of view, our Gaussian might look like this. It's a Gaussian sphere in this case. And it's a sphere that we totally enclose the Gaussian surface, or in this case, Gaussian sphere. I'm just going to say surface because it doesn't have to be a sphere. It can be anything, but you can always mold it to match the distribution of your charge, or match the shape of your charge distribution. Now, the other thing we can see about the symmetry here, so we said we matched the symmetry, and we placed it basically through R, place it so that the surface goes through. That doesn't make sense. I meant P. Place it so that the surface goes through P. R is a vector, a position vector, so it's not going to necessarily go through that. But P is a point, so you've noticed I've placed it so it goes through that. So if I can find the field on the surface of my Gaussian, well, a couple things. I've also exploited the symmetry by placing it spherically symmetric to the charge distribution, because that means that the E field is going to interact with that surface with what we say high symmetry. That is, since the surface is centered, that means the surface is the same distance from the center of the charge distribution everywhere. So every point on the surface is that distance R away from the center of the charge distribution. So by intuition, we could, because we've already seen that, for a point charge or a circular charge distribution, we have that. So where the field lines are determined. If the charge is uniformly distributed, then the field will be constant over the surface. So in this case, we can say the same thing, that since every point on the Gaussian surface is the same distance from the center of the charge distribution, and the charge distribution is circular, that means that we would expect the value of the field to diminish from the center to point P, or to R, in the same way, so that the magnitude of the field on the surface, everywhere on the surface, would have to be the same. And the angle at which the electric field crosses the Gaussian surface is also the same. And we can figure out by symmetry what the value of that angle must be. It's got to be 90 degrees. So everywhere the electric field crosses a point on my Gaussian surface, it makes a 90-degree angle. So we don't know the value of E, but we do know that about E on the surface of this Gaussian. This is amazing. This is an amazing concept, this Gaussian's law. I've always often thought that, we don't know what was going on 120 years ago or so, 125, but I think before Einstein's equation E equals mc squared, Gauss's law surely must have been the most known or used equation in mathematics and physics. Certainly, we could say it was the most elegant. And again, I apologize that I didn't already post doing this problem with Coulomb's law, because for me, it's like a gargantuan 3-page problem. And I'm taking kind of a long time to explain this because there's a lot of subtlety with Gauss's law, but literally we'll take 2 or 3 steps to do the problem to get the answer. It's amazing. It's just incredible. So we basically, by making this distribution in this way, we can kind of steal or mimic the symmetry of the E field interacting with our Gaussian surface. It's analogous to the same symmetry of the spherical charge distribution of which the field originates. And that's the magic and the beauty of Gauss's law. So high symmetry, matching the shape, E field is constant on the surface. E field is the same value everywhere on the surface. And the interaction of the area vector associated with the surface at E can be determined because we know the angle that E makes with the surface. Now remember, the area of a surface is always perpendicular to the surface. We defined it last week when we defined flux. We said that for any surface that we have, so for example, the flat surface of this podium, the area vector, we know it's going to be length times width, but the area is perpendicular. So the area is like a vector that stands up anywhere on the surface. It can be represented anywhere, and it's perpendicular to the surface. Right. If it were a cylindrical surface, like my sky here, area vector is pointing out radially away from the surface like that, from the cylindrical surface. For the top and bottom sides, if it's enclosed, the area is perpendicular to those surfaces. So points up for the top, points down for the bottom, points radially outward for the cylindrical portion. Always perpendicular to the surface everywhere. For a spherical charge distribution, same thing. A is perpendicular to the surface and points out radially everywhere. So now we know the magnitude of the area for the sphere is 4 pi squared, but the direction of A everywhere is going to be parallel to E. Because everywhere on the surface, A is pointing out radially. Right? Guess I could put something here, like doing something like that. These lines, I just chose to do the side view, but these lines also, you could make them, that would give it a little bit more of a 3-dimensional kind of perspective, but it also would make it a lot more messy to have something kind of coming out like that. Right? And something kind of coming out like this. And just add that all over, but you can see it's always going to get it more messy. I want to just kind of look at just the side view. Now, apply Gauss's law to that Gaussian right there. So what is Gauss's law? Gauss's law states that the electrostatic flux through a surface, a closed surface. Well, like, yeah. Well, it just says, yeah, electrostatic flux through a closed Gaussian surface is equal to the total charge enclosed inside that surface divided by epsilon naught. That's Gauss's law. The way I teach this is I usually evaluate the left side first, and then once I get that all done, I go to the right side, and then I solve for E. Now, the way we write the flux over here is that it's the integral. We know that flux in general is E dot dA. But when we have a closed surface, we put that closed signature over here. It's a circle around the thing. And down here, it's S. We put S for surface, meaning enclosed surface. Later on, we'll do something called Faraday's law, which, sorry, screw that. Sorry. Forget what I was about to say. Yeah. What? I think I need some tea. Yeah, sorry. I was going to say that with some integrals, line integrals, which is Faraday's law. So yeah, so now consider what I was about to say, because I'm about to say it again. You'll see this circle with a C down here, which means contour for line. And it's kind of like an analogy to Gauss's law, but it's Faraday's law. But so don't confuse that for those of you who have had or just doing calculus 3 now or whatever. Maybe those of you have who haven't. I don't know why I yawn like this in the morning. So annoying. I'm not even sure we know why people yawn. I heard all these hypotheses, but I don't know if when I was in school, they said we didn't know. I don't know if we found out yet or not. Anyway, yeah, so that's Gauss's law, and that equals charge enclosed inside the Gaussian over epsilon naught. Now, we have to do, always you want to evaluate a dot product inside an integral before you start working the integral. Now I have E dot dA. Now here, I probably had a little bit of a kind of basically when we're applying, again, just we've done this before. I did it for a surface, but let's just review. I did it for a flat surface when we were doing flux. Let's come over here and take a little kind of sliver. Now, actually, we have to take a, yeah. We're taking an area sliver. So we're like on the surface of, oh gosh, the surface of the charge distribution. And it's like this dA here is like some, I don't know what kind of geometry we're going to use. I'm going to use like some kind of like if I took a little square, consider a little square on the surface. So that's not the whole area A. And I know I represented A here as the whole area. I can do that if I'm talking about the whole area. But if I'm just talking about a small portion of the area, then it's just a dA. But still, the direction is going to be perpendicular to the surface of that little differential area. So again, if I were to draw a field line at that point, it's also parallel to that dA, perpendicular to the surface, because both the direction of A or dA is also perpendicular to the surface. So two perpendicular lines, for a sphere are parallel, irradiating from the surface of a sphere. So again, as I've shown here, if I showed an E there, it would be right along that dA, that line. So basically, when you work out this integral, that electric field and that dA is what we're dotting, what we're taking the dot product of. So what we are actually doing is the integral over a closed surface of E, the magnitude of E, the magnitude of dA, times the cosine of the angle between them, which is 0 degrees. You know what? I'm going to come over here. Get that. Didn't need to draw that since I drew it again. Yeah, so integral over the closed surface of E, magnitude of E, magnitude of dA, cosine of 0, and that equals the total charge enclosed divided by epsilon naught. You know, sometimes you see a summation sign out like this because it just implies that you've got to add up all the charge inside. And usually, sometimes charge is discrete. Here is continuous, so I guess I shouldn't put a summation. But it just means that I'm going to keep it like that because, you know, it means that the total charge enclosed inside the Gaussian. And the ENC means enclosed. So cosine of 0 is 1. So I get integral of E dA equals charge enclosed divided by epsilon naught. But as we said, E has the same value everywhere over that surface. So E is a constant of the integration, and it comes out of the integral here. So I have E times the integral over the closed surface of dA equals the charge enclosed divided by epsilon naught. But the integral of dA is just the total area A, which I could write in terms of the radius r naught. Well, actually, sorry. Ooh, that's a big mistake. I always seem to do that. We got to be careful. I'm going to write like a big G here since I almost did that. I don't know why. I just, oh my gosh. I've been misleading y'all. Sometimes I start this problem by finding the electric field on the surface, in which case I would have made my Gaussian right on the surface. That's the next problem we're going to do. And somehow I had that in my head. Essentially, I should have been at the Gaussian doing everything that I said. But it doesn't change anything because it doesn't change any of the symmetric results because, as I said, the Gaussian surface is also spherical. But maybe it's kind of better I did it there because it's the same arguments I would be doing, but at the Gaussian surface, because that's where I'm trying to find the electric field. So that's where I need to evaluate Gauss's law, wherever. But I haven't really drawn. I've kind of made just the outline of the Gaussian surface here, because if I kind of draw it in and try to make it so that you can see like a film of the surface, it's going to get really messy because this charge distribution is under it. But all that stuff, and you wouldn't be able to tell anyway. Like if I drew this little dA, if it were actually on the surface of the Gaussian, you wouldn't be able to tell because we're not at you can't see the side view. So it could be a distance r out, or it could be right at r naught. You wouldn't be able to tell. And the argument that I made, that since E is, basically the area of the Gaussian, that's really where I should have been. The area of the Gaussian is also, radial, also perpendicular to the surface everywhere. So it's the same argument, that I was making with the area associated with the charge distribution. And that's in the second problem here. That's what I'm going to have to do anyway, because I'm going to have to shrink the Gaussian down. Remember, I told you, wherever you want to find the field, that's where you have to place the Gaussian. So in the second problem, where I want to find the field on the surface, I have to kind of shrink wrap the Gaussian down to where it's the size of the spherical charge distribution. And then everything I just said is now associated with a Gaussian surface, but it's also associated with the surface of the charge distribution because the Gaussian surface is on the surface of the charge distribution. So just hope that's not too confusing, but basically I haven't really lost anything. But the point is that whenever you're doing this integral here, you're always working out the area of the Gaussian, not the charge distribution. And there's only a certain times when that's going to be the same. That is, the area of the Gaussian surface and the area of the charge distribution are the same. And when is that? Well, that's when you're trying to find the field on the surface, so that you put your Gaussian surface on the surface of the charge distribution. But right now we're a distance r greater than r naught, so we're kind of outside of that, and the charge is completely immersed inside of our Gaussian. But still at this point, we still have this result here. But the integral of dA, where dA is the area of the Gaussian, is just the area of the Gaussian. And since the radius of the Gaussian is r, then the area of a sphere is 4 pi r squared. So that's what the answer we get here for this area. I'm going to go ahead and erase something. Guess I'm done with this. The last step, remember, is just going to be solve for E. And we'll do that when I get to it. So from equation 5 over here, E times 4 pi r squared. And again, that result is, you can just write it down, right? Because technically that's a double integral to do that, because it's 2 dimensions. But we don't even have to do it. We know it's just, we just say the area, the area is going to be A, this A here, that's it, which is the area of a sphere. And since you know the area of a sphere, just write it down. Now, the other side over here is Q enclosed divided by epsilon naught. Now, before I solve for E, I'm going to go ahead and get what that is. Now, we kind of have to work on that a little bit, because I didn't give you the charge. I gave you the charge density. So we want to do a little bit of finesse with that, just to make sure we understand how to get the total charge. Because you could write the answer in terms of the total of the charge density. But remember how when we would do that with Coulomb's law, and then in the end, I would say, well, we could keep it like charge density, or we could just write it in terms of charge. Well, technically, we don't know the charge, so we have to use the charge density to, technically, this answer should be in the terms of, and we'll do that. But then in the end, I'm going to flip back and just put in the definition of charge density, again, just to show you, get the result in terms of the total charge so that we can compare it to a point charge, the kq over r squared. So the definition of charge density for this thing, rho naught, is equal to its total charge over total volume. So that's going to be charge, over volume. And the volume of a sphere is 4/3 pi r cubed. So that means, sorry, for total charge, I'll just say charge. And that is the charge enclosed, so I'll just do that. And I'm just going to write, I'm going to take this symbol off. I think it's a little confusing, but it's just the total charge enclosed. Well, yeah, okay, I'm going to keep that just as a formulaic kind of definition. But then the charge enclosed is just the total charge on the thing. So I'm going to do charge. Yeah, there I could just say the total charge Q, whatever that is a total, either that or Q total or something like that. But I'm going to put a capital Q. So actually, let's do it like this. Let's say total charge enclosed. And down here, this is going to be the area. And it's the area of, it's just the area, so the volume. It's just the volume of my charge distribution. So volume. But that ends up being the total charge on the thing, Q total, divided by the volume, 4/3 pi r cubed. So that I don't know why I'm getting so hung up on symbols here. I guess because in the end I want to write it as total charge. Yeah, I want to stick with the symbol. So I'm going to go back to what I said originally. Sorry. Just to keep the symbol so you don't get mixed up. So 4/3 pi r, sorry, r naught cubed, r naught cubed. So that the total charge enclosed is equal to 4/3 rho naught pi r naught cubed. Now I'm going to stick equation 8 into 6. Yeah, so 8 into 6 yields that E of 4 pi r squared equals, I've got the 1 over epsilon naught is still there, so then times 4 over 3, and then rho naught pi r naught cubed, all that over 1. So now when I solve for E and divide this thing through, I'm going to have E for r greater than r naught equals 1 over epsilon naught times 4 over 3 rho naught pi r naught cubed, but then that's going to be over 4 pi r squared. Yeah. I'm going to separate out. So in this result, on the left side, there's only one thing that's a variable. Look, the 1 over epsilon naught is constant. 4/3 is constant, obviously. Rho is a constant because the charge is uniform. Pi is constant. R naught cubed is constant. And on the bottom, 4 pi constant. The only thing that's varying is r squared. Now it's constant, or the r. It's constant for this. It's the same argument I was making with Coulomb's law. It's constant for this particular problem. But in general, it varies because we can show the that's an arbitrary position. We could have been any place outside of the charge distribution, any place that's greater than r naught. So we could kind of write that as a variable in a sense, like separate that out. I like to do that. So I might do like the 1 over r squared over here someplace. And of course, you can simplify too. The pi's can go out. I want to keep them in just for a minute though, because I want to. So that's really my solution. And then you can make it a vector, right? Put the vector symbol on here and do a little radial unit vector symbol over there. I could take this epsilon naught and kind of put it under here, or maybe take this 4 pi out. That's what I'll do. Yeah, I'll take the 4 pi out because then that would be 1 over 4 pi epsilon naught, right? So that's just k. So we could rewrite this finally as in terms of E r greater than r naught basically equals k sub E. And then this stuff here is just the total charge, 4/3 rho naught pi r naught cubed, and then basically times 1 over r squared, r hat. But remember that thing right there, see, that's just the charge enclosed. But if I were to call the charge enclosed Q, just whatever the total charge is, I couldn't. So this is my solution here. I'm basically done because I have it in. Whenever I give a solution, I like to give a solution only in terms of the given quantities. And the only given quantities are rho and r naught. So that satisfies that. That technically is the answer. Now you can see it has the inverse square law, right? That's the only variable, and it's 1 over r squared. So that's it. But just to make it look pretty, since I know that I could define this equation 8. That's what I was kind of getting mixed up with over there, but I didn't want to do it too soon, or I don't know. I could go back and just define this as the total charge Q, because it is. And so when I then take that and put that in, this is what I'm going to have. I'm going to have everywhere outside of the thing. So again, everything in parentheses here just becomes Q total right here. So E r greater than r naught equals k Q total over r squared r hat. And you can clearly see from that's a point charge, right? That has the classic kq over r squared. Now, I told you 2 or 3 steps, right? And actually it doesn't look like that because I was teaching, so every little detail I was pointing out. And also, I just want to point out how sophisticated the law is. And I think I mentioned this, I don't know whether it's probably like Ian, it's probably mechanics. I don't think I mentioned it this semester, but let me do it now. When you talk about elegant equations, like E equals mc squared, Gauss's law, what you lose in rigorous mathematics, you gain in subtlety and power or complexity. And I'm defining power and complexity. Well, in this case, whereas power in mechanics is energy per unit time, I'm going to define power, kind of what I mean by this qualitatively is information per whatever you encapsulate that per language. So like with poetry, that's why poetry is more powerful generally than prose, because you can store information in the rhyme and meter, not just the words. And also the poetic nature, because you're doing analogies and all these kinds of things, alliteration, all these English tools can have meaning, right? Um, describing the context of the situation. In our case, the language is mathematics. So here, Gauss's law, but now the mathematical symbols are taking on complex meaning and they're storing information about the problem within that. So whenever you go to something that's simpler, usually mathematically, it takes a lot more finesse to understand how to apply it properly than if you were just using, Coulomb's law is like a hammer, like a sledgehammer, just bamming out, until you get the answer. Things like Gauss's law, that's not the case. It's the opposite. It's just finesse and subtlety, and you get the answer simpler, but there's a lot more intuition and context and subtlety that's involved. So all these little details, like once you do the problem a couple times, I already know the answer because I'm setting it up to be that way. I could have just jumped from this step basically to somewhere over here, because I can see that if I know what I'm looking at, that the integral of E dot dA is going to be just E dA. And E will come out. All the things I said in step 4, I could have just jumped right down here to step 5. I could have gone from here to here. Now, I generally don't like to do that because I just always want to make sure I'm taking a little bit of mental energy and going step by step, because I have such a terrible history with careless errors and missing minus signs and things like that. That I take my time and I usually do each step like this. I don't really, no, this is a bit much over here, right? Like I probably would have gotten down here and just said, jump from here to either over here or maybe just whatever to down here. But still, that's 2 or 3 steps if you put them all together, as opposed to 3 pages of, integral. Like if you do Coulomb's law, this is a triple integral, and it's like crazy, so yeah. I'm sorry, I was up all weekend, all night, finishing up this report. I had to get in today for our annual review of the program of the physics department. 5 o'clock last night. Got 15 minutes to break. Okay, but the fact that we went through all of that like that really carefully, we got the payoff now. We got the payoff because I mistakenly kind of initially qualitatively evaluated basically at the surface, but in the second problem, so this is for problem I, right? This is the field outside for R greater than R naught. But for part I or double I here, where I'm at the surface, well, it's the same argument I have here, all the exact same steps, except that when I get down to the final step here, my R squared is actually R naught squared, because R equals R naught. So as opposed to redoing the problem and everything I said, I can just take this solution right here and stick and make R, well, I guess go back to this solution here and make R squared equal R naught and then simplify. and I just write down the solution. So I'll do it in 2 steps just to be clear. So from 9, so this is yeah, so that solution was K sub B 4/3 rho naught pi r naught cubed, and here I'm just going to write here, over r naught squared. R hat. Now, the r naughts cancel. Well, 2 cancel here, leaving 1 here. And so my final solution oh no, it was in the cat. My final solution over here for that thing is going to be K sub B 4/3 rho naught pi times r naught. Now, I'm not going to do any transform back to Q at this point, just because it doesn't, this is a constant. Everything here is a constant. So that means that the electric field on the surface is constant. And that just proves what we already knew. We knew that, right? Because I didn't say it like that. What I said is that the electric field is the same value. Well, I kind of did. It's the same value on the surface. So I said it was a constant of the integration, and it comes out. Well, this is proving that it's a constant, and that's the value of the constant. And it can still be a vector. It can still point radially outward, but it just has a different value at that on the surface as it does on, anywhere else, inside or outside the surface. And so that's the answer. I'm going to leave it at that. That's the answer for part 2. Didn't even have to do any work. Wrote it down. Now, well, if people were in class, I would make this a working break right now. We'd set it up and go to break and not let you work on it. But since nobody's in class, I'm just going to finish it before our break, about 10 minutes. Now we want to basically have to go back and do the problem on the, on the inside. And by the way, again, whenever I did the Gaussians, I didn't redo the problem. I told you because I didn't want to have to. We did everything, but basically that's the situation where I would have taken the Gaussian and draped it right over the surface, and then everything I did is the same. And there, this little, when I was looking at dA on the surface, that this would have been that problem. But again, it doesn't really change anything, and I can just mathematically, qualitatively, it doesn't change. I would apply Gauss's law the same way, but the final result is that I would get, this guy instead of what I got down here for equation 9. But there is some fundamental, not fundamental difference, but in terms of the left side of Gauss's law, that's going to be the same. But when we go inside, evaluating epsilon, evaluating the charge, it's going to be a little bit trickier here, because we got to remember that when we're inside at a radius less than r, we don't have all the charge enclosed. We don't have the total charge of the distribution enclosed, only partially. Let me show you. So here, if I redraw the distribution here, it's circular, uniform, right? All the charge is not just on the surface, but everywhere throughout the volume of the thing. So, in fact, I should make it bigger. I should make it bigger. Okay. So when I enclose this guy like this, inside from my radius less than r, you can see I'm not getting all the charge. The only charge, so now this is a radius r naught, or r, excuse me. And I still have my radius r naught, which is the big thing. Here. I know my spheres are kind of janky. So my point is that I want to find the whenever you apply Gauss's law, you can only find the field on the surface of the Gaussian surface. So my field that I'm going to find is a distance r away from the center of the charge distribution, which means that the only charge that's contributing to the flux of this inner Gaussian is the charge inside here. All the other charge on the outside doesn't contribute to the flux. And we proved that, right? We already proved that because we showed that, we said that whenever the source of a charge, whenever the source is outside a closed Gaussian, it can't contribute. The analogy that I gave you was like a chicken wire container. If I make a box out of chicken wire and I have the source of some flux like water, like, so I take let's say I'm on a farm and I have a water pail, you know, those old classical water pails that look something like this. And it was like some sort of half front here, and then you have a little water thing coming up like that, a spout, like that. I don't know. And then you have a handle over here. I don't know. So I take that thing, you know, to make the water come out kind of like a shower thing. So here's and just assume, you know, pretend that this is chicken wire, this box. Disregard this thing here. And so I take the water pail and I pour it. Well, what's the water going to do? It's going to come in the top, then going to go out the bottom. And here, that's negative flux up here, positive flux down here for that water drop. And all the water drops, whatever goes in is going to come out. But if I were the source inside the thing, check it out. Let's say that I took a water spigot and I somehow stuck it up inside the thing and I turned the water on. Well, the water, there you're gonna definitely have flux, non-zero flux, because the water comes out and then it never goes. Like if the water took this path, went out, then you only have flux coming out of one surface, and so nothing is that's flux, right? So it's not going to cancel out. But what if it even goes up and comes back through? Let's count the times. It's like the negative sign. Double means positive, even means positive, odd means negative. In this case, even means no flux, odd means flux. So in this case, if it took that path, that's out one surface. If it goes straight up, out once, comes back in, cancels that with that flux, that's zero, but then it goes back out the bottom, and then there you go. You got flux. So whenever the source is inside, it doesn't matter what happens, you're definitely going to have flux, right? So that's applicable here. All of the charge inside the Gaussian there we know will contribute to the flux. And even though we have a whole bunch of charges on the outside here, I'll put them in green on the, we don't have to worry about those. They're not going to contribute to the flux because whatever flux they contribute, they're going to cancel out. So we can say this stuff, no contribution to flux. So the thing is, we have to figure out how to get the total charge inside. Now, just as to help you, we had Gauss's law right here. The left side of Gauss's law for this problem is all going to be the same. We get the field lines are going to be coming out radially for our Gauss. All of it's the same. So we could just, again, we've already done all the work. So we could just skip down to the left side over here. And just write down that over here we have E. And again, the area, I'm going to drape my Gaussian surface, well, that is my Gaussian surface, and it's spherical. So the area of the Gaussian surface is still the same thing, 4 pi r squared. On the left side, I have 4 pi r squared. But on the right side, I've got to figure out what's the charge enclosed inside the Gaussian over epsilon naught. That's what I'm working on right now. So that's what the argument is. Well, it's pretty, I can use logic and a ratio to figure it out. I guess I can erase this now. That the total charge enclosed, I can do a ratio of volumes. Because the total charge enclosed, since the volume charge density is the same, the total basically is a constant. So that it's not really a ratio. I guess it is a ratio, but it's just using the definition of charge density. Because I can say that rho naught is equal to the total charge enclosed inside my Gaussian divided by the volume of the Gaussian. But that's got to equal the total charge divided by the total volume of the whole thing. So I can kind of group these things together here as an equation and solve for charge enclosed. So let's do that. We'll call this equation 14. So then 15. I'll call this, volume with R naught, because that's the total thing. So that says that the charge enclosed equals total charge in this ratio of volumes, V of the Gaussian over V of the charge distribution. So the total charge enclosed in terms of the total charge, period, it's going to be equal to, so it's going to be 4/3, 4/3, 4/3 pi r cubed over 4/3 pi r not cubed. Of course, the 4/3 pi cancels out. And in the end, I've got that the total charge enclosed inside my inner Gaussian, r less than r naught, is equal to q total times this ratio of r cubed, which is a variable, divided by r naught cubed. So I have to take equation 17 and stick it in here. So total charge enclosed then is equal to, sorry, no. $17 into 13. So I get that E, E equals, well, I had E times 4 pi r squared is equal to basically this thing divided by epsilon naught. So that's going to be 1 over epsilon naught times Q total and the ratio of the r cubed. Actually, I'm going to do it like this. I'm going to put r naught cubed here because this r, again, this is a variable. And this is not. These are constants. Not quite done because remember, I still have to divide through by the area of the Gaussian over here, 4 pi r squared. And yeah, I'll do that over here. So this would be 18. And then equation 19. So my E is going to be equal to, that's going to be a 1 over 4 pi. I'm going to put that with the epsilon naught. So 1 over 4 pi epsilon naught. I still have a 1 over r squared here when I divide it through. So over here, I'm going to have this Q total over r cubed is still there. Then I have the r cubed, r not cubed, r cubed over r squared. And how about that? Look at what we get. That's surprising. That goes, that goes. So it goes to it's linear. The variable E is now, E is proportional to R, not R squared. That's very helpful, particularly when you evaluate the electric field at the center, which we know what it should be, like the electric field at this point. At that point, you can't enclose any charge for an infinite small point, so according to Gauss's law, if the charge is 0, then the field should be 0 there. But for all those other solutions, this guy and, well, that guy's a constant. So those solutions don't lead to what the field is. Basically, if we add this, we get an infinite electric field because we're dividing by 0, right? Remember, this is the variable, 1 over r squared. But here, that works out. So that's going to be K to be Q total over r not cubed times r hat. So it's a linear function on the inside, and that it's great because at the origin, well, at the center, where r is 0, well, you just put 0. You don't get a delta function anymore. It doesn't or blow up because r is 0, so E is 0 at that point. And this is the field. So everywhere inside, the field is linear. Everywhere outside the field of 1 over r squared, everywhere on the surface, the field is a constant. Yeah. Yeah. So those are the three regions. In fact, I can emphasize it here by saying r less than 20. So E r less than r naught equals. Yeah. So this is a classic physics problem. Every book will have this or some version of it. And I've done everything. Like this is all there. I've done all the steps for every, every part. Well, actually, there's one other step I can do. It reiterated what's happening, as you move from origin out to infinity. But what we can do is graph it to show that a graph. Again, math is the language of science. So the best way to explain what I just say is to show a graphical rendition of the electric field versus distance from the origin versus r as we go from r equals 0 out to r equals infinity. So that graph will look something like this. And again, it's going to be in your book somewhere in the chapter. They're going to show it. I graph E versus R. On the horizontal axis is R. I'll make that R hat the unit vector. And this is E. And let's make this value here R naught. So 0 out to infinity. So the graph, and I've got the three different regimes. Inside, on the surface, in fact, let's make the surface, let's draw a dotted line through R naught so that and make it red so we can easily see it. R naught. That line there. And so we know that at R naught, the value of the field is this thing, is a constant. So I'm going to just come here and say at that point, that's got to be what I know that this guy is this thing. I just write it like that. Just write out what it is. Need more space though. A, E, 1/3. All this, rho pi. Oh, I guess it's just this thing, sorry. Why not? So that's the value at the surface. And let's make the regimes 1, 2, and 3. So 1, 2 is right there on the thing, and then 3 is everywhere outside. So at 2 is a constant. Inside is linear. The maximum value has got to be this thing at the surface, R naught, and at 0, E has got to be 0. So basically on this graph, the field inside would look something like this. Two endpoints have got to match up. It's got to be a line. Inside, E, this is E less, this is this guy, E less than R naught. At the surface, we got that as a constant. Outside the surface, we got the inverse square law. So again, something like that looks like that is 1 over x. something that looks like that is inverse square law. So this is 1 over r squared, and it's this solution here. I'm just going to put 1 over r squared. I'll loop that in. I probably made that a little bit too steep, but you get the point. Maybe we're very far out, way far out, it will look like that. So yeah. So that's the last thing you would see on a problem like this. Break time. I'm going to go ahead and set up a problem for you. Well, so that we have a working break. And the problem is to go back and let's do a conductor, a metal, a solid metal sphere that has the same amount of charge, but actually, you know what? Let's not do that one. Let's do because we haven't talked about conductors yet. That's not until next chapter, but we'll do it then. We'll come back and do Gauss's law for the chapter on potential. It's at the end of that chapter too. Let's do the same problem, but let's say that we have an insulating shell, very thin layer of shell, same radius. We can even put the same charge. Now, we can't use rho for charge density because that's only for volume. We have to use sigma. But we could say like we put enough charge density on the surface so that if we calculate the total charge, it's going to be the same as this last problem. But it's a spherical shell, a thin, extremely thin spherical shell of charge distance sigma on the surface. And you could say the surface is so thin that it's even less than the diameter of a point charge. So, yeah. So then for all practical purposes, you could say that the charge is on the surface. And then calculate the electric field at three different regions. Outside, on the surface, and inside. So think about that as we take a break and make it take a little bit more than 10 minutes. You got to get some coffee or something. Food, wake up. Then I'll come back and I'll do that problem. And we'll do some other too. We'll do several problems. Today is kind of a recitation on Gauss's law.